to our first technical talk of the year. And tonight we've got great pleasure to have Tony Rosa, who's the head of the rail business in First Balfour. So he's going to give us a presentation about his early life in rail and tunnels, yes. And he's going to give us a history and construction overview of the Channel Tunnel. So Tony is a qualified civil engineer, over 35 years of experience, and he's traveled the world and he's acted as capacity general contractor, project management consultant on the client side. And he was involved in the Channel Tunnel in 1987, so quite a few years ago when he was a young lad, I think, yeah. And so he was seconded from Balfour Beatty to TransLink. And then since then, in the first 14 years of his career, he spent working in the civils division in Balfour Beatty, and then also worked on some other tunnels, Heathrow Express, and so on. And then he's subsequently, in the last 2 years, he's become involved in the, since June last year, he's become involved in the rail business in First Balfour. So I'd like to invite Tony to come up and give us his talk, his presentation.
Thank you very much, Mark. Thank you, PTS, for allowing me to present. So I'm going to go over, as Mark said today, a bit of an overview of the history of the actual project, its location, and also just the key points and the key parts of the actual project itself. And I know there's probably a few people in this room and also attending online who probably worked on the project as well. So give you a bit of a setting here now. Cast your minds back to 1987. I just freshly graduated from university and I was looking for my first employment. Somebody said to me, yeah, I think this company is looking for somebody to, some engineers to go and build the channel down in Kent. And I thought, wow, they've probably already got their engineers, you know, they've probably already got their team, everything's set up. There's not much happening for me. So, but I give it a shot anyway. That was my vision of the Channel Tunnel. A couple of platforms, a hole in the ground. So that's why I thought maybe, you know, it didn't really require that many people to work on the project. Little did I realize the immensity of the project I was going on to. The scale of it to this very day, it still remains one of the largest engineering feats last century. Right, just to give you a bit of an overview now. So it just gave you an idea as well of how green I was when I graduated from university, you know. Green, just like the Kent countryside, Garden of England, or as green as the jungles here in the Philippines. Very green and naive. Right, for those who are not so familiar with the actual location of the channel, it's actually an arm of the Atlantic Ocean. It's located between France and England. The closest point between the two land between France and England is about 37 kilometers. It's between near Dover and Calais. It suffers from strong currents. It is also affects the ferry crossings when there's adverse weather conditions. It's a pretty tough environment to sail, and it's often, you know, it's been a focus of attention in terms of bridging between mainland Europe and England for trade purposes. The top left-hand corner there, that gives you an idea of the sort of the shipping traffic that goes through there. See, about 600 cargo ships and about 60 ferry ships travel through on a daily basis. That's not to say all the actual tourist boats as well that go out on the weekends. So very heavily trafficked and impacted obviously by the adverse weather conditions. Top right, give you an idea of the proximity between France and England. You can actually see across the water on a clear day. It's just a matter of going underneath it. And 1909, bottom left-hand corner, Mr. Blériot flew across that channel. And you get the occasional people who like to swim it as well. That's a bit of a personal challenge. That's not me, I can assure you. The other means of transport were the hovercraft as well. Right, so on to a bit of history now. So it's been a project that has been in the minds of people for quite a few hundreds of years now, dating back to as early as 1750, with the Academy of Amiens that actually launched a competition. It was actually won by a French engineer at the time, but nothing actually came of it. It was sort of died a bit of a death. 1802 was the next one that was tabled, and this was to actually dig a tunnel underneath the channel, under the seabed, with horse-drawn carriages. And there are going to be two tunnels. One tunnel to actually deal with the traffic, and the other tunnel underneath to actually accommodate the actual water that will be seeping into the tunnel. Wild? Maybe not. I don't know. Anyway, that was proposed and presented to Napoleon, but I think at the time, you know, sort of there's still a few differences between the countries. So I think England felt quite exposed. You have to think as well that this channel represented a good line of defense to the country itself. 1856 was the next one. That one there actually took on a same principle as before. It's going to be two tunnels. And this would actually, the solution was actually going to be proposed where there'd be meeting on an island between France and England. That one there, if I'm not mistaken, well, that was actually backed by a number of the banks, the Rothschilds, and thousands of actually investors, and was actually, well, actually, there was the next one. Sorry, apologies. So I didn't actually participate in any of these projects, just to be sure. But that one fell through. 1880 was the one that was actually started, and they dug about 2,000 meters either side of the channel, but the English were dead against it, simply for reasons that they felt as though they would be exposing themselves to an invasion. So that was knocked on the head. 1973 was the next attempt at actually breaking that barrier, bridging the two countries. That one as well did actually start digging as well, but at the time it suffered from funding because of the oil crisis, and both governments were investing heavily in the actual Concorde, and that was drawing a lot of money, and so eventually that was knocked on the head as well. Interestingly enough, the TBM that was used on that section of tunnel was actually then partly removed during the project that I actually participated on. Then there's another attempt in 1979. The two national railway companies put themselves together to propose a solution, but that didn't actually materialize either. So there's been many attempts over the years, but eventually in 1984, the British and the French governments decided that they really needed to get something built in order to improve the trade between the two countries. So they launched a competition. There were 9 solutions that were actually presented. 4 were shortlisted, and the eventual winner was, in fact, what was called Eurotunnel, was the group called Channel Tunnel Group and France Manche SA. And that was the solution of the actual tunnel for the train and shuttles. There was various other solutions in terms of a suspension bridge, combination of bridge tunnel, and a tunnel which was a road and a railway. So 1986, the Treaty of Canterbury was signed, and that effectively laid down the legal, the financial and administrative basis on which the project was going to move forward. One of the key things here is that there was going to be no government funding and public funding whatsoever. So this had to be entirely privately funded. So, actual project location now. As I indicated before, the project is actually located between the northwest of France and the southeast of England, Kent and the Pas-de-Calais. fundamentally different in terms of their geographical layout, topography. Northwest of France, fairly flat. And from a population perspective, it really wanted to attract the tunnel to that part of the world, simply because they saw it as an opportunity to create employment. The high unemployment rates in that part of the world, heavily industrialized, but they wanted something like that to regenerate the industry. Southeast of England, in contrast, was fundamentally different in that it's hilly, there's cliffs, as you can see from the pictures here, the White Cliffs of Dover, and Kent is called the Garden of England, and you'll see from these pictures here that there is a good reason as well. It is a very picturesque county, some very pleasant parts, and heavily opposed for a variety of reasons. One was effectively the threat to the ferry industry and the people that are employed in the ferry industry. They felt as though they were going to be undermined. The other one were the environmentalists, because they envisaged that this tunnel was going to destroy the beautiful English countryside. And also, I think many people were still concerned about suddenly bridging mainland Europe and England, and felt exposed potentially to immigration issues. Anyway, so big efforts had to be focused on those aspects there in terms of especially the environmental aspects, safety, and so on and so forth. Okay, so winning group was the Eurotunnel group, which composed of, it had to be primarily an Anglo-French cooperation, since both governments were supporting this. They had to obviously get French and English banks, as well as the contractors from both sides of those, both sides of the water. So originally, the group was one, and they eventually realized that they had to separate the owner-operator from the actual contractor because there was a potential conflict of interest. So what happened then was the creation of the Eurotunnel group, which would be the ultimate concessionaire for 55 years initially. And the actual contractor was a series of contractors from France and England. Translinked from the English side and Transmanche from the French side, giving TML, Transmanche Link. They were overseen by the Intergovernmental Commission Safety Authority. They were there to primarily make sure that the safety standards, the design, the operational aspects were respected. And so they also employed maître d'œuvre. Maître d'œuvre is effectively the engineer, to make sure that the technical requirements were actually met, bearing in mind that this is a design, build, operate, and transfer project. So it was designed progressively as the project went along. The Transmanche link was effectively structured in a manner that both sides, from the civil side, the French and English had their own organizations. However, the common elements were the administrative side in terms of the actual services, so as admin, finance, commercial, the engineering as well, in terms they wanted uniformity of the engineering throughout the actual project itself. Same with the actual transportation group itself. And this group, at its peak, employed about 14,000 people. I started in 1987. It was still a very small organization, and it gradually grew after that into this enormous project. And as you can see, there are numerous stakeholders, numerous interfaces, numerous interests that had to be maintained progressively as the project went along, and obviously was part of the challenges of the day-to-day we're having to deal with. I'm a young engineer, so my main focus was primarily on-site, theodolite, working with the subcontractors and the contractors. So, but I didn't have the sort of levels of contact at the higher levels anyway. So in terms of the actual tunnel itself, and this is, I'm going to ask you to pay attention because I'm going to ask you a question later on. Well, I'm going to challenge you and see whether you paid attention. The tunnel itself is the third longest tunnel in the world, after the Gotthard tunnel in Switzerland and the Seiken tunnel in Japan. However, it does hold the record, which is actually the longest underwater section. So the key thing to remember here, it is not in the water, it's not suspended in the water, it's actually under the seabed. So under the seabed, running through at anywhere between 45 to 115 meters below the actual seabed. The deepest section of the channel is the Fosse d'Angers, 85 meters deep, which is above the line of the actual tunnel itself. The geology that was really identified as the ideal tunneling medium is a chalk marl, which is effectively like a chalk, but with traces of clay and silt in it. Ideal tunneling. The English side suffered less in terms of fissured rock and water ingress, but on the French side, there were actually incidences of water ingress and high pressure, so which had to be dealt with. Hence the different tunneling methods used on both sides. On the English side was open face TBMs, whereas on the French side were EPBMs. The structure of the actual tunnel itself consists of two running tunnels, the trains running in either direction, divided by a service tunnel and with cross passages and a pressure relief duct. The cross passages are at every 375 meters and the pressure relief ducts at 250 meters. The pressure relief ducts serve as structure to help relieve the pressure at the front of the train when they're traveling through at 160 kilometers an hour, and also help relieve in terms of the pressure at the tail end of the train. Otherwise, if you don't have these, you would be ending up with an excessively heated environment and also an inefficient train system running through using a lot of energy. In the tunnel, there are also two very large crossover caverns, very large, long, wide, and high caverns, which serves for the purpose of the construction, but also in the long term for eventual operation of the actual system itself. You have to remember this is a fully integrated transport system, not just the tunnels. We're working to, so we're already thinking about, you know, the operation of the trains. If they have to shut the tunnel down, they'd move the trains onto the opposite track. Okay. Right. In terms of schedule, I think when you realize what was actually built in this time, the immensity of it, not too dissimilar to some of the projects at the moment that are being talked about in Manila, like the North-South Commuter Rail, in terms of 7 years or so. This was actually built in 8 years. So here we're talking about design, procure, build, test and commission, and then a fully operational tunnel system at the end of it. And I had the fortune of working on it from 1987 through to 1994. Key thing to look at here is the actual overall layout of the actual transport system. Left-hand side, you have the Folkestone terminal, which is where the shuttle trains loop around, come and unload and load the vehicles, the trucks, passenger cars, and so on. Shakespeare Cliff was effectively an operational area that was used to start the tunneling from seaward bound and also landward bound. Moving along, you have the crossovers in the tunnel. Sangatte shaft, which was the equivalent of the Shakespeare Cliff, but on the French side, slightly different configuration and setup, but it was also the operational shaft from which they did the tunneling seaward and landward. And then a Cocquelles terminal, which was effectively the same as the Folkestone terminal, except that here, this was more in open land. Okay, and on the right-hand side, anybody who worked on that project will probably remember that schedule. And critical here was, in fact, the service tunnel, which was the first tunnel to be excavated effectively was acting as the pilot and the probe to understand the ground conditions ahead of the two running tunnels as they were digging those. So as there were a very large number of boreholes, about 120 marine boreholes and about 70 land boreholes that were drilled to do ground surveys, they obviously had to make sure that the tunnel didn't hit any of these. They had to be blocked up prior to the actual tunnel. But the service tunnel, a service TBM, was used then to probe into the ground either side of the tunnel to assess and make sure there's no water ingress. Unfortunately, there weren't any floods or major floods anyway. Okay, so one of the key aspects that really made the success of the project, apart from the actual tunneling itself and the crews, was the actual supply chain, and that is paramount in these types of projects, is to make sure that your supply chain is on top of the game and it's not holding up the TBMs. The tunnel segments were fabricated in two areas, one on the English side at the Alagrain, and the other one in France near the Sangatte, near the Cocquelles terminal, or Sangatte shaft rather. I'll go to the French one first. Sangatte was probably easier to build the actual facilities themselves because of the lay of the land. It was actually very close to the shaft. You didn't have that many logistics issues in terms of transporting the actual segments to the actual tunnel. Whereas on the English side, the challenges were a bit greater. As mentioned before, as I said, Southeast England, hills, tight spaces, cliffs, and so on. Very difficult to have a setup that you can see on the top right-hand corner, which was the Alagrain facility. 8 production lines producing over 1,000 units a day. So it was decided to make use of the available land of the Alagrain. Aggregates were shipped from Scotland by ship, and then the segments, when they were actually constructed, were actually transported by train, because adjacent to the actual site itself was a railway line. Slightly different configuration in terms of the actual tunnel segments, simply because of the geology as well. As mentioned before, on the French side, it was fissured rock with water ingress. So therefore, they had to use gasketed concrete segments. On the British side, less so. For cross passages and the pressure relief ducts, the cast iron or SGI segments were actually used as a lining to the tunnel. The two main operating sites that I highlighted earlier on, which was Shakespeare Cliff and Sangatte. Shakespeare Cliff actually made use of the original site that had been set up in the 1800s, 1880s, which had partly been created to do the original tunnel dig, and then was subsequently also used for the 1974 one. But this had to be expanded because the amount of space and equipment that had to be used and delivered to the actual site meant that at Shakespeare Cliff, there was about 1.8 kilometers of land in length that was actually recuperated. Seawall was built, and the tunnel spoil was actually used to fill this site to then build your pit head above the ground, as you can see there, top right-hand picture. Top left-hand picture is the actual Shakespeare Cliff during the earlier stages. The top of the cliff was the actual site offices. For the right-hand side of those site offices was actually the accommodation for the actual workers. Thousands of workers working on the project. They needed to be within close proximity of the tunnel. And from a logistics point of view, they accessed the tunnel through a shaft, for those going from the top of the cliff, about 115 meters deep. And from there, they accessed the tunnel. So it's a complex underground system, interwoven tunnels that had to deal with ingress of materials, plants, movement of trains, spoil removal. It was very impressive structure. Bottom left-hand corner, you'll see the segments starting to build up as well on the Shakespeare Cliff before they're transported underground to take to the TBMs. French side, slightly different configuration. They had the benefit of a fairly flat, open plot of land, which they built a 66-meter diameter shaft. And they used that as the logistics shaft from which to actually launch the TBMs, supply the segments, do the spoil removal. Very, very ingenious in terms of structure. And there they used the three tunnels, service tunnel and running tunnels. They launched the TBMs seaward and northward and landward bound as well. Those sites were eventually used to house the actual chilling and cooling buildings that were necessary to actually ventilate also and cool the tunnels. And although it doesn't look like it, but this actually became a nature reserve at Shakespeare Cliff called Sunfire Hoe. You may recall I mentioned as well the Folkestone and Cocquelles terminals, and this is effectively the terminals that were located at either end of the actual network for this transport system. This is where effectively the vehicles were loaded and unloaded, and the trains passed through. And here are located the actual substations to power the tunnel. The thing that's to notice here as well is that both sides of the tunnel were actually powered by these substations, but in case one of the substations went down, it was able to actually provide the necessary power to the traction system for the trains, as well as the actual auxiliary services, which was the ventilation and cooling. The interesting aspect of this particular site on Folkestone was in fact that when I started there, they had to raise the land by about 6 meters, and the way to do that, to avoid a logistics nightmare in what was effectively inhabited area, you could see to the left-hand side was Cheriton. They decided to pump sand, which was dredged at Goodwin Sands. It was brought in by barge, and there's a very large pipe that had to pump up the sands into that area there to build it up to the right level, and then the water was drained off. So it was pumping up about 65 meters in difference in level. The other key features of the terminals were in fact apart from the loading and unloading platforms, the operation and control center, but more importantly, bottom right hand corner, you can see a big loop. That's effectively where the shuttle trains come back on themselves to load and unload, or unload the vehicles and then reload before they go off on the next journey. France, because of the availability of land, they could build this on the surface. In Folkestone, it was a 1.1 kilometer long portal frame cut and cover structure. My first job actually. Very interesting prospect. This was part of you have to remember, this was part of an integrated transport system. So you're building all the different components at different times in parallel, and they all bits of the puzzle come together to be able to have an operational railway at the end of it. So it's actually paramount that all these moved ahead in tune and to respect the overall schedule. French side, because of land availability as well, had the maintenance sheds for the actual shuttles. So not to underestimate some of the actual the systems that actually go into the tunnel. In order to ventilate and cool these tunnels, there's some very large fans either side. And a very large cooling system as well. Another one of the projects I actually worked in. This was the benefit as a young graduate engineer. You're moving around on the different projects within the actual overall program in the space of 6 years, because generally they're about 1.5 to 2 years, so you can actually move around. I also had the benefit of working on the commissioning of the actual pumping stations that were designed to evacuate water in case the tunnel flooded. So I used to cycle out to the middle of the channel, in the tunnel, clearly, to oversee and interface with our French counterparts for the commissioning of the substations. And all these various technologies and systems and rolling stock are actually controlled by two operation and control centers either side of the actual tunnel. Now, you can imagine to get this up and running in such a short space of time is the sheer number of subsystems and overall system to be working. So there were about 900 different subsystems that needed commissioning to make it fully operational. And I had to go through the various phases, commissioning of the subsystem, then dry run, wet run, and then effectively the full operational tests, which was quite a complex process in terms of, and obviously had to respect all the necessary safety standards, because some of the main concerns on either side, from both governments' perspective, was in fact the concern and safety of passengers and the actual safeguard of the actual infrastructure because of eventual flooding, fire, and so on and so forth. And it did, fires have occurred and they've had gone through repairs. But yeah, those are sort of aspects that needed to be taken into consideration as part of the overall construction of the project. So, just to, and I've flown over this, but it's a very large project, as you can imagine, but all this for what? This is the trains running through a tunnel up to 160 kilometers an hour with a headway of three minutes. So tunnels are important, but you also have to look at the actual overall system itself, okay? Typically now, well, there are about 400 trains traveling every day through the tunnel. The latest information that I have as well is that GetLink, who are the actual concessionaire, now for 99 years, not 55 any longer, the concession was actually extended, is that they're looking to actually pass over 1,000 trains through the tunnel. The other thing is that has been useful is that this tunnel actually is the medium through which they've fed cables to actually transfer power between the two countries. And this effectively has been a source of revenue for the concessionaire. This wasn't there originally, but this became, as I mentioned, tunnels now, you know, you can extend your the purpose of it and actually rent out space to other entities. So, as mentioned there, 6 to 7 hours to get from Paris to London or the other way around. Now, about 2.5 hours of the actual benefits. And the trade invariably between the two countries and Europe has increased, notwithstanding Brexit and COVID. And this is what it looks like when you travel through the tunnel. No? No, okay, right, okay. So, I was, as a young graduate engineer, I was actually invited to a public information evening to which members of the public attended, and we were meant to be informing them about the progress of the tunnel, the purpose it served, and so on and so forth. And I was approached by a member of parliament whose first question was, well, you know, when I'm traveling through the tunnel, will I be able to see the fish? I had to be polite. I said, if we see the fish, we've got a problem. Anyway, yes, I thought it was also to see whether you were paying attention as well when I mentioned that it's actually under the seabed. And this must have been, when I watched it earlier on, it actually brought a bit of a lump to my throat. It did bring back a few memories.
At 12 minutes past 11 this morning, we watched French tunneler Philippe Cosette pick up his drill. At 12 minutes past 11 this morning, we watched French tunneler Philippe At 12 minutes past 11,
It was working fine, wasn't it, earlier on? It was, wasn't it? Do you want to?
At 12 minutes past 11 this morning, we watched French tunneler Philippe Cosette pick up his At 12 minutes past 11 this morning, we watched French tunneler Philippe Cosette pick up his drill. On the other side of the wall, of chalk only a few inches thick, his British counterpart, Graham Fagg, was drilling too. We knew they were making history, watched live on ITV, by breaking through the wall between the British and French sides of the tunnel.
You'll notice that the French were very
On the other side, his British counterpart, Graham Fagg, was drilling too. We knew they were making history, watched live on ITV, by breaking through the wall between the British and French sides of the tunnel. They're through, they're through. We've all been waiting for Mr. Fagg and Mr. Cosette. The French
And that concludes my presentation. Thank you very much.
Brilliant. Thanks very much, Tony. So, we've got a little history lesson there and also some insights into your early years. You've obviously had a great grounding in tunnels from that start, from that project. So I think we've got a few minutes. We can take some Q&A. So anybody here in the room who wants to ask any questions of Tony about his experiences, and maybe you don't know everything about the tunnels, but you can certainly answer some questions. So yeah. What type of equipment did you use?
Oh, yeah. All I remember, the manufacturer of ABB Flat were the actual ventilation fan providers. But I can assure you I did. Yeah. And honestly, I can't remember the specs of the actual equipment, but certainly the actual provider of those fans. There were two parts.
Go back here.
There was the ventilation building down on Shakespeare Cliff, and then there was the utilization of the north ventilation shaft, which was actually made use of the actual original access shaft, which the fans were then installed. But the actual spec of the equipment, I would have to feed that to you on a separate note.
Just a quick question. Were all the TPMs left inside, or did you take any out again?
So interestingly, the English TBMs, from what I recall, were actually driven off to the side of the tunnel and left underground. The French ones recovered. I think one of the French ones is actually sitting off a roundabout somewhere up in that area there. So you should be able to see it. I think it's a service tunnel TBM. TBMs were supplied by a mixture of Robbins, Howdens, Robbins, and a Japanese Kawasaki, I think, at the time that the combination of Robbins and Kawasaki were producing the PBMs. Yeah, so some of the TBMs were left underground and others were recovered.
Why would they leave such expensive equipment underground?
The purpose for leaving it underground, I don't know the actual selection in terms of the financial value of it at the end of the day, or in terms of the physical, removing it, whether they felt as a benefit. I mean, it's not unheard of. I mean, it has happened elsewhere, isn't it? You leave the skin in, you remove out the main components, but you leave the skin in as part of the lining and then build around it. So, but there's a specific purpose as to why they're. I wasn't party to that.
You mentioned about the outlet and the inlet shaft. What was like are they diaphragm walls?
You mean on the French side, on Sangatte? I don't know the full details of the Sangatte shaft. I know there was a 66-meter diameter shaft, which was eventually as well had to be protected by a membrane around it because of the inflow of water. They wanted to reduce the inflow of water into that shaft and also avoid drawing down the water table for the local population, the proximity of the actual shaft itself. This was a few years ago now.
So there's another question on the Zoom about another question about water leakage. So any problems with water leakage during the tunnel construction, and how was it resolved?
So there was some water leakage on the English side, from what I recall, but how it was actually dealt with, I'm not fully aware. French side, yes, there was, and in fact, the tunnel segments were actually designed to accommodate that. The way that segments were actually installed on the French side was actually within the skin of the tail of the actual TBM, and then pushed out. I think the British side were using an open-face TBM, which could use grippers on the side of the tunnel, which was a slightly different configuration in terms of setting up a water ingress, grouting. I don't know what the full details are on that.
I think you said that the pilot tunnel or the other smaller tunnel did some pre-grouting and ahead of the main tunnel drives. So that probably controlled the grouting. I mean, the water inflows quite well. Any other questions? Any online? No? Another one. Another question about progress. So, what's the sort of tunneling rates that were recorded on the project? Do you know them?
Yes, so generally 300 to 500 meters per month, and I think the records of about 1,000 meters in a month.
Excellent. Okay, any other questions? Any final questions?
I think that was pretty much very close. There were some minor delays, some changes in the actual design itself, which also resulted in an increase of the cost of the project because a number of design changes were required by the safety authority, in particular for fire protection on the actual trains themselves. Originally, the trains were actually open all the way through. They actually then wanted fire doors installed, and there's a number of actually design changes that obviously focused on design on the safety of the passengers and the infrastructure itself, which resulted in an increase of the cost.
One more question.
Tony, like in the UK and in France, there's a long history of tunnel construction, subways being constructed. Now here in the Philippines, we're just starting. It will be our first time that there will be a subway tunnel project in our country. Are there challenges here in the Philippines that the ones in the English Channel did not have, or it's basically the same? Yeah, I suppose the channel is much bigger, but you know, it's our first time here to have a tunnel project, a subway project.
So well, I think challenges and here is you're talking about tunneling it in an urban environment, which is fundamentally different to this type of environment. But the challenges, whether it be the workforce, I think the local population in terms of the workforce itself have worked internationally, and you'll probably find that we'll probably be able to employ a lot of the people with tunneling experience that have worked overseas who want to come back home and work in the Philippines. I think the challenges will be maybe the actual sheer number of projects that are going to be taking place simultaneously, and in terms of the capacity of the workforce and in terms of the capability of finding the workforce to be able to undertake those work. Thereafter, in terms of the equipment, the equipment that's going to be used for the tunneling itself, these are tried and tested and improved and have been over the years. I don't think there's any sort of real issues there. It'll be the logistics, moving around Manila, obviously a heavily congested city in terms of spoil removal and moving materials in. I think there's going to be challenges there compared to some of these, but I don't think they're insurmountable. There's often a solution for most of these. So, I think we're confident that these will be a success in the Philippines.
To add to that, there are a lot of really good Filipino tunneling engineers around the world. And if there's a chance to bring them back and they want to come back, then, the opportunities in tunneling in the Philippines is good for them, to be honest. Obviously, one other thing the Philippines suffers from is earthquakes. So earthquake resistance and design loading for earthquakes is something that's quite, needs to be catered for in the Philippines. We know that the tunnels really perform quite well during earthquakes from Japan and other places. So actually being underground can be quite resilient in terms of the performance of tunnels. So, that's certainly earthquake loading that needs to be thought of in the Philippines more than the UK. Okay. Okay, if no more questions, then I'd like to thank Tony for his fantastic talk tonight, and can we do that in the usual way? Thank you. Okay, thank you. Okay, thank you very much, Tony. Just, I got a few slides here just to, hopefully this will keep working. No. Okay. So the good news is the bar is sponsored tonight by First Balfour. So please enjoy the bar, the drinks. So that's a good reason for Tony to be here to support that, and we thank First Balfour for the sponsorship. Next slide, please. So we have a program for technical talks over the year. We're starting to get some slots already put forward. Iwata-san did say that he would do something. So we've got him down to do some tunneling in Hong Kong, mixed ground and so on. And then there's an interesting talk in April from Brian Shepstone, who's going to talk about his experiences with bombs in Hong Kong and how to deal with them in excavations and in construction. But we still have a few slots available later in the year. So please, please let us know if you want to do that. You want to give a talk to the Tunneling Society. Next slide. So we have organized, you probably remember, Noda-san gave us a presentation last year on the Davao bypass. So it's taken a bit of time, but we've managed to get a slot to take some people down to go and see that construction project. So we're organizing a visit to leave on the Friday the 10th to Saturday the 11th to go down, go into the tunnels, going to get a tour around the project site. We have the place is limited to only 15 to 20 people, right? So first come, first served basis, and the price will be approximately 5,000 to 6,000 per person. We're not sure yet whether we're going to book all the flights for everybody, because you might want to go and do something different. But certainly for the accommodation and for the transport, we've got that all organized. And then maybe in May, we're going to try to organize a visit to Corregidor, to the Malinta tunnels. So we try to do that in May to go and see those historic World War tunnels. Next slide. So remember to pay your subscriptions for the year. So if Malcolm was here, he'll be saying that. It's not come out yet, but it's coming soon. So you'll be getting your invoice to be sent out soon. So please give us your subscriptions for the year. Next slide. And then other social activities we've got. We're teaming up with the Philippine Mining and Exploration Association. So Joey is here tonight with us, and we're trying to collaborate with them. We've got some slots at their golf day. So we've got a team of 3 teams. So if you want to join, please sign up under the Tunneling Society umbrella. And then obviously later in the year, we should have Oktoberfest and the Christmas party at the end of the year. So with that, I think that's the last slide. So with that, thank you very much for coming tonight. And thank you for those people online. And please enjoy the drinks and the snacks provided by First Balfour. Thank you very much.